All right, this is the third supplement for today, and we have another disassemble example program here. This is one of the things that we have seen before. I am not going to make any program any more difficult to debug or excuse me, to disassemble than it really is already by messing up these label names. In other words, I'm going to keep the label names as meaningful label names so that you don't have to kind of deal with that part too. Alright, so let's take a look at this program, and remember in the previous supplement my recommendation is to focus on the jumps first, because those are the most easy ones to identify. So the JMPs, and also if there's any, in this case we don't have any, but if we have any conditional branches, those are important as well. So what we need to do here is to kind of go through this code, find out all the jumps, and figure out the context of all of those jump instructions. In this case, this is the first one, so we'll just go kind of go in a sequential order. Excuse me. I hope that didn't break your speaker or your headphone, because it looks like it's pretty loud on my scale here. So anyway, this is the code to do the stack initialization, which we really don't have to represent in C code. So you can just leave this one alone, but knowing that we are using register D as the stack pointer is going to be helpful. We have a label of main, which is basically just marking the entry point of the actual main subroutine. So that is, just kind of traditional, because nobody's actually branching to the main label. So it's really just for documentation purposes where the starting point of the main subroutine is. And then we go to this jump instruction right here. So this jump instruction is jumping to the label 5, which is, because it's set up here. So these two instructions are really just continuing execution at the label 5. And then before that, we always have to kind of focus on what is before these two and see if that makes any difference. So before, we have some stack operation, because this is storing something to where the stack pointer points to. This is what we are storing to the stack pointer. And these two instructions together is decreasing the stack pointer by 1 or decrementing the stack pointer. So based on this analysis, okay, so I'm going to try something a little bit new with this particular one. So I'm going to combine some cells, and let's see here. So we can say this is for decrement the stack pointer by 1, and then these two together is to store return address 1 on stack. Okay, and we can always make the columns wider so it's easy to understand. And together these two is continuing execution at the label 5. Okay, so we say jump or go to 5 the label. Okay. Alright, so based on this, decreasing the stack pointer, storing the return address, and then going to another label, these three things happening in this particular order is indicative of a call. So we combine all of these and make that a call. Okay, so we go here and say merge all, and this is really just calling the subroutine 5. Okay, and over here we have, after we get back from 5, because this is the return address, after we get back from 5, we are doing kind of the same thing again. Okay, we're doing some stack operation. We are once again decreasing the stack pointer. So let's go ahead and indicate this. So decrement stack pointer. But one thing that is different is over here I use register A as a scratch register, but over here I'm using register B as a scratch register. In other words, I'm preserving register A because I'm storing the content of A to where the stack pointer points to. And register A is, by our convention, the register to use to specify the return value. So we are actually storing the return value of 5 to where the stack is pointing to. So with this one, I can now say save return value of 5, the first call to 5 on stack. Okay, so we'll specify that. Okay, and then over here we have kind of the same thing. We have a decrement of the stack pointer. So let's go ahead and do this. So we are allocating more stack space here, and over here we can see that we are free to use register A again, because now that we have saved it on the stack, it is no longer, we don't need to save it anymore. So with these two instructions, merge cells, we are storing, store return address 2 this time on stack. So when we store the return address, which is somewhere in the to continue code execution, that's a very good indication that we are calling a subroutine. So combining with this last part here, we know for sure that we are making a call. So we format this, merge cell again, and then we say go to the label 5. So once again, when you see the allocation of stack space, storing a return address, which is a future point in execution time, in code execution, as well as the eventual branch to the subroutine. When you have all three components, they together is specifying another call. So I look at all of these lines and then say, okay, I can recognize these as another call to 5. There we go. All right. So at this point, we know that we have called 5 twice. This is the first time, this is the second time, and I'm saving the value of the first call in between. Okay, so that means by the time I get to this instruction, register A has the return value of the second call, because that's the convention that we use. Register A specifies the return value of a call, but this is the most recent call, and that's why register A has the return value of this thing here. The return value of the other call is still on the stack, because that's the last thing that we push on the stack. The return address that we pushed here onto the stack, that we saved on the stack, is no longer here, because the subroutine is responsible to deallocate it after it makes use of that for returning. So that means at this point, this is we are loading the return value of the previous call, or the first call of 5, into register B. So we just kind of comment here. So we say B is the return value of first call of 5. And A already has the return value of the second call, so what we're doing here is adding those two. So we add return value of first call of 5 to the second call of 5. Okay. And then over here, this is it. I mean, this is basically just adding those two. In other words, in C syntax, we are just adding the return value of the 2 calls to 5. So that means over here, I can now specify what it is actually doing. So let's merge the cells, and then we say register A is 5 plus 5, because it is the result of the first call to 5 plus the result of the second call to 5. Okay, and these two are here because now the stack has that one extra thing, which is the return value of the first call to 5, which we have utilized over here. So typically, after you make use of the content that has been saved on the stack, we typically should deallocate it. So right here, we are adding 1 to D, which basically is deallocating that 1 byte so that it is quote-unquote available. Even though we don't have anything else to do at this point, we really should do this. Okay, so we basically deallocate byte used byte on stack used to save return value of the first call of 5, but I'm not going to write all that. And the halt instruction is the end of main. Okay, so we can just write here and say this is end of main, because there's nothing for main to return to, so the halt instruction really marks the end of main. So now we have the subroutine called 5. Okay, and we can tell that this is the starting point of a subroutine because we have a call to 5, so we know that 5 is a subroutine, so this is the beginning of that subroutine. And it doesn't do much. Okay, so let's go ahead and figure out what this code is doing. So B is what the stack pointer points to, which is the last thing that we push on the stack right before we call the subroutine. And then over here we are these two instructions is to add one to the stack pointer. Okay, so we'll combine these two and just say that we are increment the stack pointer. When you increment the stack pointer, you are deallocating the stack. When you're decrementing the stack pointer, you're allocating bytes from the stack, because the portion of the stack that is in use is where the stack pointer points to, and everything that is above that to a certain point. So this is to deallocate that byte that is being used here. So we kind of scan a little bit forward and see that we are using the jump instruction is using B. So we kind of know that this B is the return address. Okay, so this is a return to caller, because whenever we pop or we get an address from the stack and eventually use it for a jump, it is basically a return address, and this is indicative that we are at the end of a subroutine. So what makes this subroutine a little bit tricky is how we also put a value into 5 right after the branch, right before the branch. So in this case, we know that register A has a special meaning for subroutines that return a value. So this one is for specify a return value of 5. Okay. So in other words, this chunk of code is not just returning from the subroutine, it is also specifying a return value of 5. In assembly code, we definitely have different instructions to deal with different portions of this. But in C, this is all done by one single statement. So in C, this is how we do it. We say return 5 and a semicolon, and that's it. So once we have all of these components, then we can now say that this is the beginning of main, and the return type of main really doesn't matter because we are not returning anything from main. And then decrement pointer, we have a 5 call here, we have another 5 call here, but the actual thing that we're doing with those two calls is to specify A equals to 5, the first call and the second call to 5, or the return values of those. So A equals 5 plus 5, like so. And that is the end of main, so we use an end curly brace to represent it. Or if you prefer, you can also say halt is the same thing as exit 1, and then we have an end curly brace. And then here we have the beginning of 5 as a subroutine, but because 5 as a subroutine has a return value, we can see that it makes use of register A in this way. So we can now say it is int. We don't have to worry too much about the width of the int here, so we just specify int 5. It doesn't take on any parameters. And this is the end of 5. And in between, we just have that one single C statement of return 5. And that concludes the disassembly of another program. So I hope you find this useful, and I'm going to stop the recorder now.